In this chapter, we study the competitive port pricing problem. Multiple ports compete for the same shipping lines and cargo flows, and pricing decisions directly reshape market share. The goal is to choose prices that protect long-run profitability, not just short-term volume. A small shift in share can translate to millions of dollars, so pricing strategy is a core competitive lever. The scenario is a battle for the hinterland. Three major container ports in a regional cluster compete for the same customers. Each port must balance revenue per container against the volume needed to reach economies of scale. If one port cuts its container handling charges by 10%, the other ports must decide whether to match, undercut, or hold position. The right response depends on price sensitivity, capacity, and the competitive landscape. Pricing competition is difficult because ports are differentiated. Service offerings, reliability, and operational efficiency vary, so customers do not respond to price alone. Decisions are interdependent. Your best price depends on competitor prices, demand segmentation by shipping line, and capacity constraints. That is why we need a structured, tiered toolkit, rather than an intuitive, one-off decision. This chapter uses 8 tiers. Tier 1 builds a mixed integer baseline with market shares determined by a logit choice model. Tier 2 uses iterative best response to search for equilibrium prices. Tier 3 uses a genetic algorithm for multi-objective trade-offs. Tier 4 uses deep reinforcement learning in a multi-agent setting. Then Tiers 6, 7, 8, and 10 expand to distributed autonomy, human and artificial intelligence collaboration, ethical constraints, and proactive market shaping. Tier 1 formulates pricing as an optimization problem with explicit demand allocation. You decide prices for each port and each shipping line segment, and the model predicts how demand is split. The objective is profit, margin per unit times allocated volume. Constraints ensure demand is conserved, ports do not exceed capacity, and prices stay within allowable bounds. This slide defines the sets and parameters. Ports are indexed as a set of competitors, and customers are indexed as shipping lines or segments. Each segment has a total demand measured in 20-foot equivalent units. We also define a cost to serve each segment at each port, and a price sensitivity parameter that controls how strongly market share responds to price changes. The decision variables include the price charged by each port to each shipping line, the volume allocated from each shipping line to each port, and a binary service indicator. Operationally, the service indicator reflects that some ports may choose not to serve a segment, or may be unable to serve it due to capacity or commercial strategy. The objective is to maximize profit across ports and segments. Profit is the price minus the cost multiplied by the allocated volume. This matters because lowering price can increase volume, but it can also destroy margin. The model captures that trade-off explicitly rather than relying on intuition. The logit allocation equation is the core market share mechanism. It says that each segment splits demand across ports according to an exponential function of price. As price rises, the exponential term decreases, so that port receives a smaller share. The price sensitivity parameter controls how aggressive that shift is. Demand satisfaction ensures that for each shipping line segment, the allocated volumes across all ports add up to the full demand. This is important because it prevents the model from creating or destroying demand. All the demand must be served somewhere within the competing cluster. Capacity and service selection constraints connect economics to operations. If a port does not serve a segment, the model forces the allocated volume to be zero, and each port has a total capacity limit across all segments. This captures the reality that pricing decisions must be feasible given terminal throughput and resources. Price bounds prevent unrealistic outcomes. Each price must remain between a minimum and a maximum level. In practice, bounds reflect regulatory constraints, contractual structures, and the need to avoid extreme prices that would damage long-run relationships with shipping lines. This visualization summarizes how prices translate into market shares. Use it to interpret competitive dynamics. When a port lowers price, its share rises, but competitors respond. The key lesson is that market share is not a fixed number. It is an outcome that depends on the full pricing vector in the cluster. In the concrete example, 3 ports compete for 2 shipping lines with demands of 10,000 and 15,000 20-foot equivalent units. The price sensitivity parameter is 0.01. For shipping line 1, costs are 80, 85, and 75. If prices are 120, 115, and 125, Port 1 receives 3,287 units and earns $131,480 profit from that segment. Tier 2 models pricing as an interactive game. Each port looks at competitor prices, computes its own best response, updates its prices, and then observes how the market share shifts. The purpose is to find a stable outcome, close to a Nash equilibrium, where no single port can improve profit by changing prices unilaterally. This flow diagram highlights the operational loop. Initialize prices, compute demand shares using the logit allocation, update each port's best response prices, and repeat until prices stop moving. In real pricing teams, this is the discipline you want. Never assume competitors stay fixed. Always anticipate reaction and plan for the equilibrium you are steering toward. This code section typically defines the state of the game. Current prices by port and segment, cost to serve, segment demand, and the price sensitivity parameter. It also defines the logit share calculation that turns prices into allocated volume, because without allocation there is no profit signal. This part usually defines how a best response is computed. For each port, it tests alternative prices, recomputes market shares, and evaluates profit impact while holding competitors fixed for that step. It then applies the update, often with a step size or damping factor, to prevent oscillation. This section typically implements the convergence check. It measures how much prices change since the previous iteration and stops when the change falls below a tolerance. It also logs iteration by iteration profit and share, so analysts can see whether the process is converging smoothly or cycling. In the reported example with 3 ports and 3 shipping lines, the algorithm converges after 23 iterations. The equilibrium prices are shown per port across 3 segments. The resulting total profits are about $1,247,520 for port 1, $1,189,340 for port 2, and $1,312,180 for port 3. Tier 3 treats pricing as multi-objective. You are not optimizing profit alone. You also care about market share stability and strategic positioning across segments. Genetic algorithms are useful here because they can search a large discrete space of segmented price vectors without requiring gradient information. This slide shows the evolution loop. Represent a pricing strategy as a chromosome, evaluate fitness, select strong candidates, apply crossover and mutation, and iterate. In pricing terms, crossover mixes segment-level strategies from 2 candidates, and mutation introduces controlled exploration, such as a small price perturbation in one segment. This code section typically defines how a chromosome encodes prices across ports and segments, and how the fitness function is computed. Fitness should capture at least 3 parts: total profit, penalties for extreme price volatility, and a balance term that discourages an unstable allocation pattern. This part usually defines selection and crossover. Selection favors candidates that are strong on the combined objective. Crossover recombines segment-level pricing, so the algorithm can discover hybrids, such as premium pricing in high-value segments and aggressive pricing in price-sensitive segments. This section generally implements mutation. Mutation is what keeps exploration alive, for example by randomly adjusting one price component within allowable bounds. In competitive settings, mutation is essential because the best strategy can change when competitors shift. This part usually implements constraint handling and elitism. Constraints enforce price bounds and capacity feasibility. Elitism ensures the best candidates survive each generation, so progress is not lost. This final code segment typically runs the generation loop and records convergent statistics such as best profit and market share variance over time. That convergence trace is what allows you to justify that the algorithm is actually improving the trade-off frontier. After 300 generations, the reported genetic algorithm solution yields total system profit of $3,847,260. Market share variance is reported as 0.0234, and the result is described as a 23% improvement over the basic iterative approach, while producing more balanced market distributions across segments. Tier 4 turns the pricing game into a learning problem. Each port is an agent that repeatedly sets prices, observes market response, and learns a policy. This is valuable when the environment is non-stationary, meaning competitors are also adapting and demand conditions change. The state includes each port's own prices, competitor prices, current market shares, a short demand forecast, cost variation signals, and capacity utilization. Actions are discrete price adjustments, such as decreasing or increasing price by fixed percentage steps. Rewards balance profit change and market share change while penalizing price volatility and underutilized capacity. This slide frames the learning loop. Ports interact through the market, and each learns from experience. The operational challenge is stability. If agents learn aggressively without penalties for volatility, the system can create chaotic price wars. This code section typically defines the environment and state encoding, including how market shares are computed from prices and how constraints like price bounds are enforced. It also defines the discrete action set for price adjustments. This part usually defines the queue network architecture and the epsilon greedy exploration policy. Exploration is necessary early on, but it must decay so strategies become stable enough to be operationally usable. Here you typically see experience replay. The agent stores transitions of state, action, reward, and next state, and learns from randomized mini-batches. This improves stability by reducing correlation in training data. This segment usually implements the target network and the loss computation. The target network stabilizes learning, which is especially important in multi-agent environments where the market response keeps changing. This part typically implements the training loop, run episodes, update networks, decay exploration, and log metrics. For pricing, logs should include profit, market share, and a volatility measure. This final code section typically evaluates learned policies against baselines such as static pricing or best response equilibrium. The goal is not only higher profit, but also fewer destructive oscillations. After 2,000 episodes of training, the deep queue network agents achieve an average reward of 847.3. One port learns to maintain premium pricing on high-value segments while being aggressive on price-sensitive segments, resulting in an 18% profit improvement compared to static pricing strategies. Tier 6 moves beyond a single optimizer. Each port runs multiple specialized agents: market intelligence, demand forecasting, capacity optimization, and strategic positioning. These agents communicate and coordinate responses in real time. The system can discover emergent behaviors that reduce destructive price wars and improve long-run market stability. This figure shows the distributed architecture. Think of it as a network of agents that share signals about competitor moves, demand shocks, and capacity constraints. The purpose is speed and coordination. Pricing decisions can move from hours to near real-time while keeping constraints visible. In the demand shock simulation, Asia-Europe trade demand increases by 40%. The agents implement a three-phase response: capacity reallocation in the first day, premium pricing for urgent cargo over the next 2 days, and strategic investment signaling afterward. The reported outcome is 89% capacity utilization across all ports versus 67% under centralized optimization, and total system profits increase by 34% as pricing volatility declines. Tier 7 combines human strategic intuition with artificial intelligence computation. Humans understand relationships, politics, and reputational risk, while the system processes large-scale market signals. Explainable recommendations are crucial so executives can understand the logic behind a pricing move and decide when to override it. This figure illustrates the human and artificial intelligence workflow: scenario simulation, decision support visualization, and automated execution for routine adjustments. The goal is not to replace executives, but to let them focus on the highest stakes decisions while the system handles constant low-level market changes. In the example, the system recommends a 15% increase for refrigerated services and explains it using shortage signals and competitor utilization. Trust calibration is demonstrated when humans override aggressive increases during a crisis scenario. In a 3-month trial, partnerships yield 23% higher profits than human-only and 31% higher customer satisfaction than AI-only. The system processes 847 competitive price changes daily, while humans focus on 5 major strategic decisions per week. Tier 8 adds ethical constraints to pricing. Profit-only optimization can create harmful outcomes such as predatory pricing, resilience risks, or environmental damage. This tier introduces explicit boundaries for resilience, fair competition, environmental stewardship, and social equity, supported by transparency and stakeholder oversight. This diagram shows how ethical assessment is integrated into pricing decisions. The system evaluates impacts on multiple stakeholder groups and generates explanations for oversight. The practical goal is governance. Ensure competitive strategy remains viable while avoiding outcomes that regulators or customers would reject. In the carbon pricing example, the framework prevents simply passing costs to customers without incentivizing operational improvement. Instead, it rewards the most efficient 25% of operations, with pricing advantages leading to an 18% average fuel efficiency improvement while maintaining profitability. Tier 10 moves from reacting to demand toward shaping it. Pricing becomes a tool to influence shipping line choices, service bundles, and even trade patterns. The approach uses behavioral economics insights and mechanism design to create incentives that improve system-wide efficiency while maintaining healthy competition. This architecture figure shows proactive market shaping, coordinated incentives, dynamic service bundling, and predictive influence modeling. The key idea is to anticipate second and third-order effects, such as how pricing influences fleet deployment decisions and route development over time. In the green shipping incentives example, a coordinated port cluster increases the share of high-efficiency vessels from 23% to 67% in 18 months. Average port revenues rise by 12%, and pricing incentives influence $2.3 billion in fleet investment decisions. The program also enables route shifts that reduce Europe-Asia shipping distance by 15% in certain seasons.